Hello, everybody. There were already quite a few talks about the upcoming Scala 3 features right at this conference. Many of that new features could be treated just as enhancements or maybe refinements of already existing ones. But among these bright new features, there are metaprogramming capabilities, which finally would be available out of the box. Of course, macros support was there for quite a long time in the form of compiler plugins. So technically, we can hardly call this a new feature, but having it among core language features is a clear sign that this feature is mature enough to rely upon. We can be sure that metaprogramming is here to stay, and then it would be evolved together with the language. So, well, roughly speaking, before Scala 3, we could say that metaprogramming was always some kind of an experimental feature. But among the metaprogramming features, all of them, there is one that is not merely an enhancement, but it's also brings something that was that we never had before. And this feature I'm going to talk about. But maybe let's start from the beginning, from the basics. What is metaprogramming in general, and when do we use it? And speaking in the most generic way, I'd call it kind of programmable programming. So you are not just writing a code that does something. Instead of this, you are writing a code that is writing a code. And as the name suggests, this meaning could be inferred by the name, and this is the reason why we have this meta prefix, where this is where it comes from. Okay, but why do we need any specific support for this feature? Anyway, we use Turing-complete languages, so why bother? We could actually do anything, almost anything. Speaking of some virtual environment, we could even do something like this. Why not generate code that does the thing what we want in any language, and just call the compiler and then call the compiled code, just like on this slide and this one. So we call the compiler, we run the result. Are we done? Obviously not. The culprit of this solution would be the maintainability. When something goes wrong, and it definitely would go wrong, we'd better be able to find and fix this bug. For example, in this case, by the way, this slide contains some error, but of course, the code is rather short, but maybe it couldn't be spotted at the first sight. So, and in this case, the thinner the margin between the generated code and the code that generates this code, the better. And here we just have some string interpolation, and we just stick some string representation of any arbitrary argument. This is not the level of integration we want to achieve. We do not want to get an error in the generated C code, then to try to identify where this code, which Scala code is generating it, and then fix it. It would be just simply tedious task. And first of all, in this example, the C compiler does not know anything about the fact that the code was generated. It's quite opposite, actually. The compiler is designed in assumption that the code was written by human, and that is why error messages are addressed to that human author. They are not addressed to some code that is generating another code. Unlike humans, our code is still better at comprehending such messages. So, when the bad thing happens, we need to map the place in the generated code to the code that generates it. So this is the code that we are developing, fixing, updating, adding new features, etc. For naive code generation, this would not work, as in this maybe too primitive and too stupid example. And also, in general, compilers are rarely available as a library that can be used by our code. So just doing this generate, compile, run chain is tedious task, like in the previous slide. All of this code should be written, and the best code that is the code that is not written, or maybe written by someone else. There's less chance to make some errors here. And another point in here why we want some special support for metaprogramming is, for example, in this example, we use languages with quite different semantics. And we are just humans. We are not very good at keeping all of different details of implementation, details of semantics or different languages in our heads all at once. So it would be better that it be not like in this example, Scala to C translator, but rather Scala to Scala. And actually, we already have the Scala compiler, which is written in Scala. So using it as a library is technically doable. Maybe not very easy, but doable. And the tricky thing is to make this usage simple for us, ordinary programmers who do not look into compiler internals daily. So that compiler is technically just a jar file, but it was never intended to be used like a general purpose library. So we could treat metaprogramming support in a language like some sort of interface to the compiler, which fills this gap between the generated code and the code it generates. Okay, for someone who has some Lisp background like me, using of these quasi-quotes and unquotes is quite a common tool, which is always within a hand reach. It can be used in macros, but also it can be used in ordinary code to do things like list interpolation and something like this. And it looks like it took Scala rather long time to adopt similar way of doing metaprogramming. And for me, it looks like Scala 3 finally get to the point when we come to as close to Lisp's macros as it possible for statically typed language with quite complex syntax as we have in Scala. Because in Lisp, we rather have lack of syntax. We are programming almost in just a raw IST. So just to simplify things a bit, I'd use some rough analogy. So in fact, we already have something which is far more simple, but which is used commonly in our daily Scala development. It's a string interpolation. For example, here, when we do write these expression like this, usually to compiler, it really means pick the first chunk of the string until we reach the, then evaluate the code, then apply the method to string, and then, and so forth repeat. And the result would be some kind of string literal. So when parse encounters this dollar curly braces sign, it switches to from just consuming characters and forming string literal back to reading expressions, and at the end it switches back. So if we be writing the parser for such a structure, we do literally something like this. Here we switch to string, quoted string parsers. Here we switch back to expression parser. Here we switch back to quoted string parser, etc. So, and similar to the string literal, when the string compiler, or rather parser, encounters these quotes, it reads a string. When compiler dotty, or maybe we should already call it Scala 3, encounters these quote and curly brace, or just quote and some expression, it means that take whatever code is within these quotes and give it to me. For string, it means take whatever characters it is and give them to me. For the string literal here in double quotes, the result value is of type string. And what do we get from the quoted code? It's a value of type expr, which is parameterized by some result t. In other words, type of the value we'll get if we evaluate these expressions that we get from quoted code. For this example, this type is Boolean, because we just, the final expression here is just a comparison. But this quoted expression like this has little practical use. For in fact, it's a constant expression. There are more easy ways to write things like this. So as you can see on this slide, we could also splice expressions inside of other expressions in quoted code, just like we splice something into the quoted string. For strings, we need, for the spliced code, there's the only precondition so that the code returns a string, or rather, it is convertible to the string. And since we are on JVM, we have toString methods, so literally anything could be injected in the string. So whatever is evaluated, then we can call toString for the result and inject it in the string literal. For the code, quoted code, we still need something more. At least we need that spliced code, like in this argument, be compatible with the type that is expected here. For example, second expression, if we try to inject expression of type Boolean where we expect some kind of a numeric expression, would fail. It simply would not compile. So as we can see, the quoted and spliced operations are kind of opposite of each other. Quote takes some code and converts it to an expr, and splice takes an expr and converts it back into the code. So the same is true for our analogy. Interpolated strings, it may be less obvious, but actually we could think of them this way. Double quotes convert a sequence of characters into a string value, while splice takes a string value and converts it into a sequence of characters that can be inserted in place, or not a string value, but any value that could be converted to string. And now we come to the phase consistency principle, which tells us that the number of quotes and splices between any given variable x and the reference to it must be equal. And we actually could illustrate this with our rough string analogy. So that here we go, we are reading strings. Here we switch to code interpolation. Here we switch back to string interpolation. And here we switch to splicing a value, so that we could place, for example, this x's and y's inside of the string in different contexts, but they wouldn't be evaluated and the value wouldn't be inserted. So the same is for quoted and unquoted or spliced code. But I'm tell more about this later. How can we use the quotes and unquotes? We could try, for example, to paste this code like this into a dotty REPL, and we'll get an error like no implicit argument of type quoted quote context, etc., etc. And that is why our example functions on previous slides required a given parameter of quote context type. We need to get it somewhere so that we can call our functions, which return some expert type. We know how to use strings we got from the quoted literal, but let's see how we can use the quoted code, how it could be used. Okay, let's try to actually splice or rather unquote, and if we remember that these convert the expression into the corresponding code at the top level, and we or at the REPL, we could see that compiler gives us a hint that this splice operation could be either done inside of quoted code. We already seen an example of this when we try to inject some expression in this something +1 in some function, or outside of inline method. Let's look what inline methods is. Actually, inline method is another metaprogramming feature that is available in dotty. Inline is a new soft modifier. It is somehow related to inline annotation we have in Scala 2, but unlike the annotation, we have guarantee from compilers that whatever is marked as inline should always be inline. It's not just a hint for compiler, it's like a hard requirement. Here you see the simplified version of log function you could maybe already seen on dotty block. So what does it when we try to call this inline function? As I've told, inline function body is inlined where at the point where we call it. So depending on the value of logging flag that is also marked as inline, so it's always known as compile time. If the logging is false, we just get the second branch of our if expression, and this call would simply turn into expression itself, 3 + 4. But if logging is true, then the first branch of the expression would be executed. The second one would be optimized out, and we'll get something like this. And given that inline methods could be recursive, it already provides some kind of interesting metaprogramming capability without even going deeper into expressions, ASTs, and so on. Here is another example from dotty block. This is a power function that is inlined at compile time. So you see that here we inline the power function with, for example, this value. And since for value 10 we get in this branch, we hit another clone to power function, which is inlined. So at the end, the result is something like this. All these inlined places where we encounter inlined calls are like unfolded at compile time. But let's get back to our quoted code examples that you already seen before. Together with inline, we could write a function that use our series of these B functions, B and B1. For we are providing an expression that should be inlined by this function. So we could write something like this, inline def B, and a top-level expression of this inline function could actually be a splice of some expert. Here it is not very interesting. Again, it's like another way to write that in fact x equals false. But let's get for more interesting example. If we call use b1, the parameter is marked as an inline expression of type int. So we, as you can see, we do splice the b1. So b1 is converted from expression to code. And here, the quoted expression, the code here, 3 plus 2, is converted back to expression. So the result of calling this use b1 would be like this. You see, when we had this $argument plus 1, instead of this, we got this expression 3 plus 2 injected there in the code. And if we pass different parameter, but still it is an expression of type int, for example, it's int variable, the result would be something like this. So this code 1z equals 33 would convert into this 1z equals 33, and then goes whatever we get from splicing the value, substituting the expression. So at this point, it looks like we got everything we need to do some metaprogramming. We can define a function that runs and returns some expression of some type t using quoted expression. And it's almost easy to write as just an ordinary Scala code, because in this inside of this quoted expression, there is just kind of ordinary Scala. There is no more artificial alien, or rather alien language like Scala C only in the first slide, or maybe even if we have Scala, it would still be unnatural to have it in the string. So, and with inline functions, we could define some front end for our macro calls and use it quite nicely. Let's get back to our string literals analogy. What can we do with string values that we still haven't done to our quoted code? We can have the string values obtained from string literals available at runtime. We could write one something equals, then goes string or string with some interpolation, and we'll get back the variable of type string, whose value would be the value of this string literal, and use it whatever we like, access individual characters, whatever. Let's see if we can do this with expressions. So when we did macros, we got these expressions of type export t evaluated at compile time. But actually, these could be postponed to runtime. In fact, it gives us an interface to the compiler we can use in our programs, that missing gap I mentioned at the beginning of my talk. So if we are going to use the compiler, we add the compiler as our dependency. Here is how we do this in the SBT, and dotty version is actually the dotty version which was used when we did compile our project. This makes the Scala quoted staging package available. Two main functions are provided here. The first one, which is shown here, is with quote context. The type is, you can see there. This allows us to actually run our functions that return an export t at runtime. Remember, we could use this b1 inside of inline function, but now actually we could call this function at runtime and get this expression of type export t back. So we have this value of export, which is of integer type. what can we do with this expression at runtime? Because we know what we can do with strings. Let's see what can we do with expressions. The first thing we could do is like this. If we could run this at dotty REPL and get back what is inside of this expression. And also I want to note, just highlighted this, that what we get back is actually a string. So this is kind of a pretty printer for these expressions. This allows us to see what's hiding behind this expression. And the second function we've got from this Scala quoted staging namespace is the run function. The run function allows us to actually run the code. If we look at the signature, we see that we pass an expression there and of some type t and get back that type t. So for here, for example, this, if we run, this is some kind of, yeah, everything is right. We've got an expression of type Boolean. We call this B1 function. We got this one inserted here, and it's not less than 1. Okay, it's fine. Let's consider this simple DSL example, which we'll use to see what else can we do with our staging. This defines some simple language to evaluate some Boolean expressions. We define not, negation, we define and, or. This bool defines some Boolean literal to introduce some immediate values there. And just to make things more interesting, we introduce some variables binding, which can bind the value x to some name. And this value would be available in some context, in some nested DSL. And the one is just a reference to this already defined value. So here is a compiler for this thing. It actually fits in just one slide. And what it does, it takes an exp of type DSL, our value for that we constructed for some DSL. Also, I've added here an ability to pass some arguments here, so that, for example, if we reference some value, first we look at the symbol table for already defined for it to be already defined inside of the DSL, or if it's not defined, we refer to this args value that is passed and to this function. And symtab is just a symbol table to keep these variables there. And as we can see, we just and the result is exp Boolean. So in general, we have an input of our type of our DSL and get back expressions which are an AST for Scala. So for Boolean literal, we just return an expression of with this value. For not, we just use negation for Boolean values from Scala. Then we substitute here the result of compilation of nested expression. The same is for and or. We just reuse Scala Boolean operations, and here we call compiler again and substitute here the result of such combinations. When we do bind the variable to some value, first we here we introduce Scala variable x. The value of it is compiled again and substituted here. Here is an expression of our DSL. And then here we do compile the body of this let binding, but with symtab, for which we have this name bound to the expression value. Let's see how it may look like. Actually, here I use just case classes to represent some expression. As you can see, we do define some variable of type y, with name y. We also reference for some variable called z, but it's not defined in this expression, so that it should be passed from the outside. And so the type, and here we get some expression. And also, I forgot to mention that we introduced some convenience function called compiled. You see, we want to pass our arguments at runtime when we do evaluate this expression. So this compiled function actually returns an expression of type function. And function is from our arguments, which defines some values of Boolean type. In our case, we would pass z here. And we define it again using quotes and splices. So we return the sum function. We can compile for given DSL, and we return an expression here. So we can convert this code into expression here and pass to compile. So CC, the value CC is actually an exp of this function type. So, and finally, we could run it. So, and result of this run function, we are running this CC. If you remember, CC was of type exp. If we run it, we just got the value of type that was type parameter of this exp. So actually, result is a function. And now here we call this function just like an ordinary Scala function. We pass the different values for that parameter z and have it evaluated just as if this function would be written in pure Scala. If this is some kind of a function that we just wrote that evaluates to Boolean value. So this result of calling the result function depends on two values. First is an expression, which is expressed in our DSL. The second is an argument values that we do pass to the resulting function. So for this toy example, you may wonder, what are the purposes of all of this? Actually, if we had written this corresponding Boolean expression in Scala, it would be just some kind of a one-liner. It's nothing even to care about. So first of all, this exp value could be not just supplied statically like in this example. Of course, you could just build this DSL using this ADT from some data that is available at runtime, not at compiling time like in this example. For example, we could load the config from some remote server, parse it, and call compiled on it and get back a Scala AST, which depends on the value that is not known at compiling time. So we started our service, then we downloaded some config, we loaded it from config file, then build this DSL, or we could even write some more sophisticated parser for our language, and have something this logic behind this expression configurable at runtime. So some data that is available only after we started to and deployed our service can say our program what to do. And after we called this run function on it, we get ordinary compiled function, and that can be called with different arguments. So that we get the function that is already a JVM bytecode. It is subject to all optimizations JVM could offer us. The hotspot would optimize it, whatever, but it was loaded at runtime. For example, it could be used in a program that loads a set of rules at startup, compiles them to a set of functions like this. And for example, if this is some kind of service, like a web service, GraphQL service, whatever, then we could use this set of functions as some kind of rule engine that tells us whether this request should be allowed to execute it or not. So that we've got some kind of rule engine that is compiled, depending on the information that is available, for example, at startup time when we loaded the configuration. And then when we use these rules, we actually are calling compiled code. And actually, I've implemented a sample interpreter for this DSL. And I made a comparison. The compiled and interpreted DSL above for expressions not very complex, just like they are, like this one that I showed to you, gives us 10 times speed up for compiled code after the JVM was already heated, etc. So it's quite amazing that we could not fight for these milliseconds on each request execution if we have our rules compiled. And also we have a benefit that compilation times for such expression are quicker than alternative approaches. For example, we could do something similar by calling some Ammonite script that defines some rules, but it is a much heavier solution. It brings all the Scala compiler up, so compilation for such solution could take several seconds and start up. And if you have many of these tiny scripts that define some behavior, the startup time could be considerable. This solution is much faster, and actually I like it. I'm waiting for dotty 3 to be production ready. And another use case that can be very promising in future when we have Scala 3 is that now, for example, we have tons of microservices. And I even heard an opinion on some internet discussions that microservices are inherently dynamically typed. And that is why dynamically typed languages are natural fit for them. And it's hard to disagree with it if we are processing some JSON for which we just know that it is a JSON. Then we do many boilerplate work just to match for, is it an array, is it an object, does its object contain some keys or not, and all this code is written by hand. But in general, the inherent dynamical nature of microservices is not true. For now, we have things like GraphQL or maybe some other schema-based interface there. The problem with these schemas is that even we have this schema available for some data, we have just two solutions: to use some kind of code generations at compile time, and then to write some additional code on this generated code. Still not perfect solution. It's not very easy to maintain, and writing these code generators is not an easy task, and sometimes we have something that is not supported by this code generation, and you need to invent something or fall back to like writing this interpreter for the schema or parts of the schema by hand. And so another option is writing everything by hand. This approach allows us to using this type safe compiler interface, like staging, provides us with a third option. We could use the information that we loaded at, for example, at runtime, at startup time, we obtained the schema for particular service, and we could generate a fast compiled code that doing some transformations for it. Because for case like some API gateway, it's quite a common task that we take some protocol on one side, protocol may have some schema, and we provide access to this data with different schema on the other end. So now we may compile these transformations. So actually it's almost done. One thing I also want to mention regarding my talk, macros are not only about code generation, they are about language transformations, but my talk covered only the code generation part. The code parsing, transforming the Scala code was completely absent. And long thing short, everything is bad here. Okay, joking, not bad, but it's like the best it can be, at least from my Lisper's point of view. Nothing much could be done here because Scala has very rich syntax, many syntactic constructions compared, for example, to Lisp, where everything is a list, and then you all you need to do is just to transform some list into another, and you are done. In Scala, if you want to write some code transformation, if you want to take some AST and produce something, you need to cover all the details of Scala language, all the syntactic constructs that are, if you would like to provide really complete and total interface so that your user could actually write anything inside of your macro. So I think that using the Scala as some kind of a backend for own language is more promising. But of course, macro support regarding this code transformation task is also matured in Scala 3 greatly. So thanks to my talk, many of examples were taken from the dotty blog. It's described quite nicely, the staging, the metaprogramming in general, so you could refer to it. And that's all. Thank you. Maybe you have some questions.
I'd like to ask a question in that case.
Yes, please.
First and foremost, thank you very much. That was a very interesting talk. I suppose most of us are, to some extent, studying how to adopt dotty in our projects. And one of the challenges we have at this time doing so in Quill is the fact that we are trying to migrate the quotation, that the ASTs and the quotation mechanism we build ourselves. That would be very useful to, a lot easier to do that with dotty. However, I suppose the biggest challenge at this point is like, how do we keep everything working with dotty and without dotty at the same time? So if you have any advice, any experience in that sense.
Sorry, no, I'm just evaluating dotty for some toy projects. I mean, it's like, I'm just waiting for it to get production ready, just to get my hands dirty and finally stick it somewhere in production. But yet I'm just like evaluating bits and pieces here and there. So I don't have, unfortunately, any advice for you on this.
Iurii, may I ask a question?
Yeah.
Oh, sorry, Iurii. It's a bit a holy war question. On your personal opinion, when dotty will be ready?
All we've heard is at the end of 2020, but to keep it our expectations safe, maybe it would be beginning of 2021, let's say it. But we already got clear message that dotty is feature complete. So it's up to developers how fast all the glitches, all the bugs would be fixed. So I'd say let's believe what Martin Adersky told, but also let's consider that software projects are never finished in time. So maybe it would be a bit later.
So it's optimistic time would be about 1 year more, yes? Plus minus.
Yes, I think so.
Okay, thank you very much.